And so it turns out to do the combinatorics, the place to start is, you'll see we need to start with matroids. And so I'll give you some definitions and examples of them. And then we'll talk about the rigidity matroid, and that's going to be something that is actually an easy consequence of a rigidity matrix. And then we'll talk about this whole classic result. It had been called Laman's theorem for a long time because the theorem Laman proved in 1970, but then they discovered the same theorem in a 1927 paper of Hilda Polisek-Geringer. So it may be undergoing some rebranding, and so that's still sort of work in progress. And then we were going to do some algebraic geometry, but we're also going to do some algebraic statistics. So that's going to be fun to see how there's an interaction between rigidity theory and algebraic statistics. Because what happens when you do the rigidity matroid, you can introduce it one way using the rigidity matrix, but another way uses the Cayley-Menger variety. So there's a really nice relation to the algebraic geometry. Then we're going to talk about Gaussian graphical models and maximum likelihood estimates that actually relate to the rigidity matroid. And then we'll talk about, basically maximum likelihood estimates when your Gaussian graphical model comes from a planar graph. And again, this will be just a lovely application of some of the rigidity theory that we've developed. So let me just think about two things that, situations that you've encountered a lot. If you teach linear algebra, you take a vector space over a field K, you take a bunch of vectors in the vector space. Well, some of the, the vectors themselves might not be linearly independent, but there might be some linearly independent subsets. And so just look at all of the subsets of S that consist of linearly independent vectors. And so, well, the empty set is, that's going to be a linearly independent set. And of course, if a set is linearly independent, so is any subset. Then if I have two linearly independent subsets of this set, and if one is strictly bigger than the other, then I can always find at least one vector in the bigger one that's not in the smaller one, so that when I add it to the smaller one, I'm still linearly independent. And that takes a little thought, but it's actually not too hard to show that has to happen. So that's something that happens when you just look at finitely many vectors in a vector space over a field. But you can also do the same thing in a more algebraic setting, where you take our same field, but then take a possibly pretty large field extension, take finitely many elements in the bigger field. And here the question you can ask is not linear independence, but algebraic independence. And of course, these might not be algebraically independent, but there might have some subsets that are. So I look at all the subsets that are algebraically independent, and I get the same thing. And of course, for example, if a subset is algebraically independent, any subset of that is, and this sort of the exchange property also holds. And again, it takes a little thought, but you can prove it without too much difficulty. So what we're looking at are two matroids. And this is an example of what we call a linear matroid, and these are the independent sets. And this is what we call an algebraic matroid, and those are the independent sets. And in general, a matroid just says you have a finite set and a distinguished collection of subsets that you call the independent sets, and they satisfy these three axioms. So basically, a matroid is anything that basically makes these situations hold. And so let's talk about the rigidity matroid. So I'm going to begin with the complete graph on n vertices. And remember, this is our notation for the vertex set, the integers from 1 to n. And then, of course, the number of edges in this is the binomial coefficient, n choose 2. But if I actually want to represent the actual edges as two-element subsets, this is a pretty obvious notation. So it says take two-element sets of that guy. And so that's the edge set. And so here our complete graph has that vertex set and that edge set. And then it has a rigidity matrix. And so that was the notation of the previous slide. But this is going to occur so often, I'm just going to drop the kn and just call it that. And And so remember what this does is I take a rigidity matrix in this setting. You just take a bunch of points that in d-dimensional space, and RQ represent the map that takes a bunch of points to these inner products, and right here, and again I'm taking all possible inner products because it's the complete graph. And the first definition of the rigidity matroid is I want to basically pick a generic configuration. And there's several ways to do it. The way I'm going to do it in this lecture is pick a configuration where the coordinates of each point are algebraically independent over Q. And since the real numbers have infinite transcendence degree over Q, I can always do this. And then what I get is I get this rigidity matroid, or I get this rigidity matrix, and so in particular I look at the rows. So that's a bunch of vectors in a vector space. So I get a linear matroid in that case. It's the linear matroid whose independent sets are the linearly independent rows of this rigidity matrix. Now, one thing you want to make sure is, so notice that this matroid depends on two parameters. It depends on the size of the graph, so that's the n and kn, and then my points q lie in d-dimensional space. So it depends on both the number of vertices and the dimension where I'm sort of making my framework. But it turns out that if I take another set of points that satisfies this, well, because all the entries are algebraically independent over Q, there's just an automorphism of R that takes one set to the other. And then from this, it's pretty harmless to see that these give the same matroid. Now, one question you might ask is, David, isn't the complete graph rigid? Isn't this boring? And the answer is yes, it's boring, but it has some interesting subgraphs. And in fact, what we're going to see is that this is actually a really rich object. And so even though it looks like we're looking at something pretty special, there's a lot of information, first of all, contained in this matrix, and then consequently in the matroid. And so what I want to do is I first want to basically take this rigidity matroid. Remember, this is the one for the complete graph. And I want to relate it to the rigidity matrices we saw in the previous lecture. And so what I do is I'm going to take a bunch of vertices. Rather take a bunch of edges. And then, so I could just regard that as a subgraph, my n vertices with those edges, but I want to be a little more clever. So what I want to do is I want to take the most efficient set of vertices for this set of edges. So I simply take the vertices adjacent to edges of E. That's what I call V of E. And then G of E will be the graph with those edges and then this very efficient set of vertices. So for example, if I'm in n equals 4, so here's the complete graph. If I pick these two edges, 2, 3, and 3, 4, then V of E, sort of the edges that are affected are that. And so G of E is just this little subgraph right here. And then here's one observation, is that, and this is where we realize this rigidity matrix is actually pretty interesting. So I have this sort of generic framework that I've fixed, and but then once I pick this set of edges, it has its corresponding vertex set. And that's going to pick out some of the elements that I'll call Q of E. Because remember, the Q's are indexed by 1 through n. And so basically, when I pick these set of vertices like this, that'll pick a subset of the Q's. So I've been looking at that. And then this, of course, gives me a framework for the graph I get from this edge set. Now, what does the rigidity matrix look like? Well, remember that it basically comes from a system of equations where these are fixed. And then sort of the variables that you plug in, these are the things that I called Qi prime and Qj prime. And so notice that this is basically what happens in row ij. And so what I'm doing, so what I want to do is I want to take my rigidity matrix and look at just the rows indexed by E. So this is a row that's where ij is in one of my edges. But then notice that the way I've set things up is that I and j are in the set v of E. And so the only sort of input variables that appear in this row correspond to v of E. And so if I sort of rearrange the matrix, if I rearrange the columns, because remember the columns are indexed by the i's and j's, so if I rearrange the columns to put all the v of E columns first, all the others are 0. Because again, you know, I only see stuff that comes from v of E when I look at this row. All the other inputs don't appear. So in fact, this one single rigidity matrix contains all of these rigidity matrices as submatrices. So there's a lot of information in this little matrix right here. And so even though it obviously is rigid, when I start looking at these guys, then interesting things happen. So that's really nice. So what we realize is that there's actually something potentially really interesting going on here. Now I'm going to sort of think, I'm going to try to think a little bit sort of matroid-wise, because when I take one of these sets, there's sort of two ways I could try to make it bigger. And so one way is what's called the matroidal closure. And so and I'll use this brackety for that. And so, because remember, this is a matrix. And so here, you know, in my rigidity matrix, I have a bunch of rows that are indexed by E, and they'll have a row span. But that row span might contain some other rows of the matrix for ij's that are different from the ones in E. So I add those in. So basically this is obviously going to contain those rows, but it might contain some others when a row lies in that row span. And it turns out that you can describe this purely in terms of the matroid. So, you know, here I'm thinking about span, but once you understand matroids and other ways to think about them, this is a completely natural operation. And, but then there's also the graphical completion. Because, you know, here I have this, you know, I have like, you know, I have E gives me this graph. So like when E was this, then I had the vertex set. And so I had, so, you know, what I call G of E was the graph shown in the solid red lines. But I just complete that to a complete graph. And so the idea is that when I take all, so I have all these edges, all these vertices, and I just take all possible edges. So I throw in the dashed one. And so that's basically sort of a graphical completion. And what happens is this is something that's purely matroidal. This is a sort of, you know, going from here to here, you know, taking a subset and making a slightly bigger subset. You know, this is an additional structure, whereas, you know, going from E to the matroidal closure, that's a matroidal thing. This is something sort of slightly extra. And it turns out that you can show that, you know, the matroidal closure always lies inside the graphical closure. And then the reason this is relevant, and so here I'm going to have 3 theorems, and I apologize for dumping all this to you at once, but it turns out that you can then characterize when is this guy locally rigid for its graph. Well, that's basically, so it turns out that because I'm in this extremely generic setting, local rigidity is equivalent to infinitesimal rigidity. And again, remember the example that I gave where these two concepts in general were different. That was a very special configuration. Once I go generic, these two guys are the same. And then the point is that, and that's equivalent to saying that these two kinds of closure operations coincide. And so, for example, if I were to, you know, if my edge set had these 5 edges, then when I did the matroidal completion, the matroidal completion would add in that guy, but also, of course, the graphical completion would add it in too. And notice that if I'm in R2, that is, and again, this is working in R2 because that's the complete graph. Yeah, so like I say, so here it's important that I'm working in R2, and but there I get locally rigid. Now here's another result that says that suppose I have an independent set. And suppose I'm sufficiently, and then I take a subset, well, that's also independent. And if it's sufficiently big, then I claim I'm going to get this kind of inequality. And that's basically, because saying when I have an independent set, that says that I'm in a situation where the rows are linearly independent. So then this would also have linearly independent rows. But when I have linearly independent rows, that's my rank condition, and that's this result right here, that the number of edges, which would be the size of f, is, in this case, it's the dimension times the number of vertices, but that's the number of vertices. And so this result right here gives us that result there. And we'll see that this is actually part of things that happen when you look at various theorems trying to characterize a rigidity. And then another one is that suppose I take a subset with less than or equal to d plus 1, well then it turns out it's just independent, and that's again because of this algebraic independence. There's just not enough room to get in the way of each other. But once I have more than that, then I'm in a situation where this matroidal, I have three questions I could ask. I have this matroidal thing, am I independent? I could also ask my question of local rigidity, and I also have this, nice condition we've seen in the first slide, and it turns out that any two imply the third. And so, for example, just as a way to think about it, let's suppose I have the first two. Suppose I'm independent. Well, that means the rows are linearly independent. Well, that's this condition right here. So that says I have the right rank. So that says the number of edges is less than or equal to something. But if I'm locally rigid, the number of edges is greater than or equal to something. So I have both of these, and so I have to get the equality. So the first two definitely imply the three, and then this is part of what you have to work out, that in fact any two imply the third. So here's this matroidal thing that really fits beautifully in these kind of questions about local rigidity, and and basically the sort of having this very sharp relation between the the number of edges and the number of vertices of the graph you're dealing with. And so let me talk about this Lahmann theorem. And so, like I say, in 1927, Hilda Polizek-Geringer publishes, on the, so I forget my German, glider rule. Is that edges? I meant to look it up. Or maybe on the, yeah, so anyway, of a plane, in Fachwerke, that's a framework. And so basically, maybe that's on the motion of a plane framework. And it was in the Zeitschrift for Applied Mathematics and Mechanics. And then Lahmann in 1970, on graphs and rigidity of plane skeletal structures in the Journal of Engineering Mathematics. And of course, he was completely aware of the earlier paper, so everybody would call it Lahmann's theorem. And it was, I think, only a couple of years ago that they discovered this paper from 1927. And remember that I have the idea that of local, minimally locally rigid, and remember that's where it's locally rigid, but ceases to be so if any edge is removed. And then Lahmann, and then the
German expert knows the answer.
A Google expert knows the answer. But it's structure.
Structure. Oh no, the structure of plane frameworks. Thank you. And thank you, Google. And so the idea is that, again, I want to be a generic framework, and the question is, when is a generic framework minimally locally rigid? And the answer is I have this condition right here, and then also, so it's a condition on the number of edges and the number of vertices, and then we also have. It's not just a condition here, but also we want to make sure that for any subset, we have the right kind of inequality. And then the proof is that you first prove that E is an independent set. And then once it's an independent set, then theorem 2. Well, theorem 2 is exactly that kind of condition. And when D is, and we're in the plane, so that's 2 and that's 3. And then again right here, we have locally rigid and independent, and so we get this one. But again, that's 2 times the number of vertices minus that, and so basically theorems 2 and 3 basically show that if I'm minimally locally rigid, then I actually have this. And of course, to prove it's independent, you have to use the minimality. And then there's several ways to prove the other one. The nicest way is so you assume that you have this one, and then you recursively can use things called Hindenburg moves and basically build up the graph from scratch. And it's a very pretty argument. So that's an example of sort of one of the classic theorems, and basically that works in the plane, but the problem is the plane is really special, and so I don't think there's any similar theorem in 3 space, and is there any hope for a similar theorem in 3 space?
I'll say something like that.
So the answer is, like, you can come to Jessica's talk and be enlightened. But now remember I said that there are going to be 2 ways to define this rigidity matroid. And so I gave you one way using the rigidity matrix. But now let's get into something that's a bit more algebraic geometry. So we have our Cayley-Menger variety. Remember, the Cayley-Menger variety was built using all possible distances. So the Cayley-Menger variety really was using the complete graph. And so and since the rigidity matrix we were using used the complete graph, the fact that this uses the complete graph, basically it's looking at all possible distances, that sounds pretty good. And then remember, this was my notation for the affine variety that's defined by basically those equations from the maximal minor equations that Cayley identified, and that's defined by a prime ideal. And if I think about these variables Lij, it's sort of representing the coordinates in this space. Basically it's so we are defining equations of polynomials in these variables. Well, then let's, so we take our quotient ring, and then we take the field of fractions, and so this is the field of rational functions. So that's just my notation for the field of rational functions on that variety. And then the point is that, so here's a field, and so basically I have the complex numbers sitting inside this really big field, and then the point is that it's generated as a field by the cosets of the variables. And another way to think about it is that the variables just give rational functions on the Cayley-Menger variety. So now I have a field, an extension, and a bunch of elements in the bigger field. So I get an algebraic matroid. And the second definition is that the rigidity matroid is the algebraic matroid whose independent sets, again, I'm going to think of them as subsets of n choose 2, and there's 2 ways to think about them. So if you think about just the actual definition, it's basically, it's a collection that are algebraically independent over C when I regard them as rational functions on the Cayley-Menger variety. So again, that's just the definition of an algebraic matroid. And but the other one is that this condition is actually equivalent because I take my prime ideal and I intersect it with the polynomial ring for just the variables from of the set of the variables I'm looking at, and it turns out that this algebraic independence is equivalent to this intersection being 0. And the reason is that if this intersection is 0, this polynomial ring injects into the quotient ring, which injects into here, and that means these guys are algebraically independent. And the converse is equally easy to see. And of course, this is a problem in elimination theory. So this says that if you had God's computer and enough time, you could actually compute this matroid by elimination theory. I would not recommend this as an approach, but again, it just shows, elimination theory it's everywhere. And so let me say a word about the equivalence of the two definitions. And so basically this linear matroid definition, and so that's by the rigidity matrix RQ, and that's equivalent to the algebraic matroid definition via the Cayley-Menger variety. And the idea is that this map right here that sends a point into here. Well, I'm in affine space. It might not be surjective. It's certainly dominating. And the point is that Jacobian matrix at a generic point is basically twice the rigidity matrix. And once you understand that, it's actually pretty harmless to see what's going on. And for example, in there's a paper by Gross and Sullivan, and they basically say this and then say it's obvious. But now it turns out that symmetric matrices are going to be making an appearance shortly. And so I want to remind us of that in the previous lecture, I computed the dimension and degree of this projective variety by using a relation between the Cayley-Menger variety and some non-zero symmetric matrices of rank less than or equal to D. And it turns out that there's a 2018 paper of Gross and Sullivan that they use a variant of this length, and we'll see exactly what the variant is, and then they use a theorem of Carolyn Euler to relate the rigidity matrix or rigidity matroid to a question in algebraic statistics. So that's actually what I want to spend the rest of the lecture on, is just going through a really interesting bunch of algebraic statistics where you ask a question and you answer it using rigidity theory, which is, I was certainly surprised when I bumped into this. And so here's our friend the bell curve. So what we're going to do is this is a Gaussian normal distribution, and I'm going to always assume the mean is 0, and so then it's just the standard deviation sigma, and so the idea is that the probability that a random variable x in the real number lies in the interval AB, well, you just take it's basically just the area. And so the probability that x is in this interval is just the integral from a to b. Here you have your density function, and so it's really just the area under the curve. And so notice that this is now a continuous statistical model. The ones I talked about previously were discrete ones, so now we're doing a continuous model. And what we want to do is we want to do an n-dimensional version of this. So how do you do an n-dimensional version of this? And so that's a Gaussian, we're going to do start with basically a multivariable Gaussian normal distribution. So what happens there is I'm in n-dimensional space, and so I now have n random variables, x1 to xn. And here, so this is the normal distribution and again, I'm going to assume it's centered at the origin. This is now the origin in Rn. And here, instead of sigma squared, I basically have a covariance matrix, and this is going to give a multivariate Gaussian normal distribution with mean 0, and that's the covariance matrix. Now, it turns out that in this setting, the covariance matrix is an n by n symmetric positive definite matrix. So for example, when n equals 1, it's the 1 by 1 matrix consisting of sigma squared. And so basically, this is the parameter that defines the model, because I fixed the mean to be the origin. And then there's a density function that generalizes the density function I had before. So remember, it was e to the minus 1/2 x squared over sigma squared. It had a sigma, it had a square root of 2 pi. And so what that generalizes to is, in this case, instead of x squared over sigma, it's x transpose times sigma inverse times x. And of course, in this case, if that's sigma inverse is 1 over sigma squared. And this again, because before I just had n equals 1, but now I get the full story here. And so that's the density function. So find the probability that something's in a region of Rn is you just integrate this guy over that region of Rn. And then this is sometimes called the concentration matrix. Now what we're going to see is that if you allow sort of the covariance matrix to be absolutely anything, it's not actually terribly interesting. You want for a good kind of statistical model, you want to put some restrictions on it. And one way to put a restriction on it is to, and that's where a Gaussian graphical model comes into the picture. So I have my usual kind of graph. So that's our, that's our basically setup right here. And so this multivariable Gaussian normal distribution is a Gaussian graphical model with graph G. So the restriction I put is I don't allow all possible symmetric positive definite matrices. When I look at the inverse, I want the entries away from the edges to be 0. So that's the restriction. And it turns out if you understand the statistics well enough, which I don't, that boils down to a conditional independent statement involving the random variables xi and xj. And so that's the setting that a Gaussian graphical model. Now, one thing you're interested in is this idea about a maximum likelihood estimate. So first, let me do it just in complete generality for the multivariate Gaussian normal distribution. So the idea is you have some observations. And then the idea is that the maximum likelihood estimate, it's a choice of this parameter, so it's a very specific choice that basically maximizes what's called the log likelihood function of the given data. So the idea is that, in a sense, you want to pick the sigma that sort of best explains this data. And the way you do it is because we're ignoring means, basically the sample covariance matrix just turns into this product. Now that's a column vector, that's a row vector. So this is basically an n by n rank 1 matrix. And so I'm adding up d of them. So, and of course, it's because it's a matrix times a transpose. It's it's basically symmetric. It's positive semi-definite. We're working over the real numbers, and because each of these individually has rank 1, I get, when I add them up, I get a symmetric matrix of rank less than or equal to d. Oh, symmetric matrices have bounded rank. We've seen that before, so we like that, and then it turns out that when I think about this log likelihood thing that I want to maximize, basically, once I have the sample covariance matrix, basically the gadget I want to do is maximize this, and the idea is I want to pick the sigma that achieves that maximum. And it turns out that suppose that I'm in a situation where I put no constraints, so I allow any symmetric positive definite sigma, and suppose that this when I do this sample covariance matrix, suppose by some miracle it's positive definite. Well, then you can just pick the sigma to equal the s, and you're done. That actually maximizes this, and so in this case, you can actually just say exactly what the maximum likelihood estimate is. And it turns out that when the number of observations is greater than or equal to n, well then, I'm basically taking a bunch of sort of random rank 1 matrices, adding them up. When when I add up more than n, I'm going to get sort of a random, symmetric n by n positive semi-definite matrix, which generically will be positive semi-definite. So with probability 1, the MLE will exist. Now the problem is that I've cheated, because what this says is that the model is the data. So this again is this sort of overfitting, and it's theoretically looks pretty, but it's actually pretty useless. And so again, what happens is that's because I put no constraints on what the the model is. And so that's where, when I take a Gaussian graphical model, I might be in this situation. This might be, positive semi-definite, but I no longer can just take this equal to that because I have to satisfy this condition. So life gets more interesting here. And so the question is, I can't do this analysis anymore. And so for a Gaussian graphical model, basically, how many observations do I need for my maximum likelihood estimate to exist with probability 1? That's the question that you ask about in this situation. And so the way I'm going to think about this is, so when I'm in my Gaussian graphical model, my observations still give me the sample covariance matrix. And very crudely speaking, what's going on is that I really only care about, or I really only know what's going on, on the main diagonal, because the probabilities is 1 there, or off the diagonal. And so what happens is that in one sense, I have partial information about and so the idea is that you have a partial matrix, and that's the part that you really care about. And so the idea is that, if this was my graph, then basically, 1, 3, and 2, 4 are the missing ones, and that's these entries. So the idea is that, sort of philosophically, this is really sort of what I have, and I don't really know much about what's going on here. And the theorem that you can prove is that a maximum likelihood estimate exists in this, for this particular sample covariance matrix, if and only if there's a positive definite matrix where when I look at the G entries, it agrees with my sample one. So what that means, a way to think about it, is that the MLE exists when I can take this partial matrix and complete it to something that's positive definite. So that's the idea about in this particular situation.
So,
but
quick question.
Yeah.
The constraints that we're imposing, are they supposed to represent forced independence of certain observations, or are they representing lack of information?
Yeah, and the answer is I'm the wrong person to ask about that. Because as you'll hear this, I simply don't know the statistics well enough to answer that.
So where's Seth's student?
Yeah.
What's the answer?
Can you repeat the question?
So the constraints, G, are they supposed to represent things that we're forcing to be, variables that we're forcing to be independent? Or are they representing limitations of the reliability of our observations or something like that? Like, I thought that it was supposed to be representing forced dependence or independence of variables, but there's these.
I would say you first learn like the independent structure, and then that that would be my thought. And then you basically know that like these things you have no idea they're like interactions.
Yeah, I think that when if it's a perfect model, if it's independent, then these things will be zero.
Yeah.
Because,
Right.
Because these two can't affect each other.
Right.
There's no sort of covariant.
And so what happens, though, this theorem, what makes it interesting is that when you sort of do this positive definite completion, there's more than one way to do it. And so then what you have to do is, of all the possible ways to do it, you have to basically take the one with maximal determinant that makes this happen. Turns out that happens to be a convex optimization problem, so that's actually pretty easy to solve. And then once you pick the one with maximal determinant, then you can pick that this has the right kind of behavior, and so you actually have what you want. And so in particular, we actually get a corollary. And so now suppose that for our Gaussian graphical model, that suppose that D is a number of observation exceeds n. Well, in this case, this sample covariance matrix will generically be positive definite. So the sigma here will, I could take that, but again, this sigma won't be the maximum likelihood estimate, but this basically gives you a starting point for actually computing the maximum likelihood estimate by an iterative process. And so the idea is that so once you have enough observations, these guys are going to have a very nice MLE. But we're going to see some examples where you can do much better than this estimate. So that's going to be sort of where I end the lecture. And so I want to talk about two stories about partial matrices. So this is a very hand-wavy thing that's just sort of my thought process about trying to figure out, why on earth does this have anything to do with rigidity theory? And because right now it's pretty stuff, but like, hey David, I thought we were talking about rigidity theory, and so what does this have to do with the kind of stuff we've been talking about? So again, our data gives the sample covariance matrix, and then again the MLE exists when I have this, so where I can complete this to a positive, definite, symmetric n-by-n matrix. And so the idea is that the MLE is sort of a matrix completion problem. But now suppose I want a framework to be rigidity, or a framework to be rigid. So I can think of this as a matrix determination problem in the following sense, that suppose I have a matrix, a framework, for some graph, and it gives I get a full matrix, n-by-n matrix of these distances, but I only really care about the ones that come from the edges. And so, but the point is that if this is locally rigid, then sort of if I have information about the edges, well, that then determines D. So what happened, and it would be up to finitely many choices, because of situations like that. But the point is that here I have a matrix. My graph gives me sort of some entries, but I want that entry to determine sort of everything else. So there's at least a family resemblance between these problems. So it's not outrageously surprising that what's going on, because basically I'm both going from a partial matrix to a full matrix. And so that's sort of the link. But there's a big difference, is that in this matrix, notice that when I equals j, it's 0. So I have zeros on the diagonal. Whereas here, that won't be the case. So so it turned out the diagonal is going to cause problems. We're going to have to sort of think about how to handle the diagonal of the matrix. But we'll see that that's solved in a very pretty way. So here's a theorem. And so again, we have this set of n-by-n symmetric matrices of rank less than or equal to D. And of course that's it'd be a nice variety. And in fact, and here it's n by n. So basically, I need the diagonal and the stuff above the diagonal, and that determines the whole matrix. So in this case, I have variables xij, but now I can equal j, because this is a general symmetric matrix, so I'll have diagonal entries and stuff above the diagonal. And then, of course, I take, I want the rank to be less than or equal to D, so I take D plus 1 by D plus 1 minors of this symmetric matrix, and that generates an ideal, very classic determinantal ideal. And then, this set here is actually the variety defined by those equations. And so that means that I actually have an algebraic matroid. So here's a theorem from Carroll and Euler in 2012. And so suppose I have, my graph, with the usual number of vertices, and suppose that I have this ideal, and suppose when I intersect it with a particular collection of variables, so I take all the diagonal entries, and then also, when I do the off-diagonal ones, I use the ones that come from the edges. Suppose that intersection is 0. Then Carolyn proved that the MLE exists with probability 1 when I make D observations for my Gaussian graphical model. So basically, the fact that I have both an N and a D is critical, because remember, N is the number of random variables, it's the number of vertices of the graph, and D is the dimension that I'm, and D is the number of observations. And so having this right here says that D observations is sufficient for this Gaussian graphical model with probability 1 to have an MLE. But of course, when I think about this in terms of the matroid, because remember, I have an algebraic matroid of this variety, the same way we took the Cayley-Menger variety and got a algebraic matroid, you play the same game, and in this case, you use the xij's, and so the point is, so what Carolyn's theorem says is that if this is an independent set in this algebraic matroid, I have the MLE. So now we have independent sets and matroids are giving us information about maximum likelihood estimates. But remember that n-by-n matrices actually are related to the Cayley-Menger variety. And the Cayley-Menger variety is the rigidity matroid. So something should be going on here. And that's what Gross and Sullivan figured out. Because remember, we got to get rid of the diagonal. And so here's the algebraic matroid of this variety of symmetric matrices of rank less than or equal to D, and again, relative to the xij's. But again, we want to get rid of that diagonal, but it turns out that's an independent set, and in this matroid. And there's simply a matroid construction. It's a contraction matroid where I simply contract the diagonal. And it turns out that, so basically you get rid of that, and then the remaining entries are the ones that are sort of above, strictly above the main diagonal, and that's exactly the set, of course, that we're interested in for the rigidity matroid. And then the way that this works is that basically a set like this is independent in the original matroid, so I put in all the diagonal elements and some other stuff, and then it's if and only if E is independent in the contraction matroid. And so a way to restate Carolyn's theorem, remember her stuff always had that, so basically E is independent in this matroid, in this contraction matroid. Well, that says this is independent in the matroid of the symmetric matrices, and then by her theorem, the MLE exists for D observations. So all I need really is independent sets in this matroid. And then the link to rigidity matroids was worked out by Gross and Sullivan in their 2008 paper. And it's interesting because, I was reading the paper, I saw that they were, going to relate the rigidity matroid to the, the symmetric matrix matroid. I said, oh, that's just this isomorphism. I was getting all excited. This isomorphism, it's a beautiful isomorphism of varieties. It completely messes up the generators. It in no way gives an actual isomorphism matroids. So it's, for things like computing degrees and stuff like that, it's great. In terms of the algebra, in terms of the combinatorial structure, it's not right. So this is where, recognizing the power of the combinatorics is important. So and notice it also sort of works differently because, in this case, I had to go from n to n minus 1. Well, here I have to go from, I keep n, but I go from d to d minus 1. So it's a slightly different way of doing things. But again, that's why, contracting the diagonal takes care of that. So they prove, and of course, remember that this is a matroid. It's a bunch of subsets of that. This is a bunch of subsets of that. So in fact, they're actually the same matroid. It's actual equality of matroids. And then when we have this, we have some really nice consequences because remember so basically E is independent here. Well, basically if E is independent in this rigidity matroid, so when you put these two results together, if I have an independent set in this, and then E is the vertex set, the edge set of my graph, then the MLE exists for D observations. And so all I have to do is produce an independent set in the rigidity matroid, and I know something about maximum likelihood estimates. So let's do an example of this. So I'm actually doing another proof. So it's 2 proofs in a row. That's very fine. And so this is one of the really nice theorems in their paper. So you take a planar graph with n vertices. Then the MLE of the Gaussian graphical model exists with probability 1, exists when I have 4 or more observations. Now remember our earlier result. Our earlier result said if the number of observations exceeds the number of vertices, which is n. So suppose my planar graph has 10 million vertices. Well then if I have 10 million observations, our earlier theorem would say the MLE is going to exist with probability 1. But now because of this theorem, I just need 4. So this is a good theorem. And so what I'm going to do to prove it is we're going to assume that, it turns out, let's assume you have at least 4 vertices because it's sort of trivial in those cases. And then the next thing I do is I basically try to add as many edges as, so I use the same vertices, but I try to add edges. I'm trying to make it a complete graph. And I do it as much as possible until I get a maximal planar graph. So I want to preserve planarity. So I don't just add all the edges, I do it as much as I can until I do this. And then I basically people have studied, if you think about it, like the 4-color problem, stuff like that. People have studied planar graphs a lot. They know a lot about planar graphs. So,
Four, though, I think.
oh, I think so, but it's still planar graphs, and so they know a lot about these guys. And so, for example, a planar graph is what's called 3-connected. So you have to remove at least 3 edges before you disconnect it. So that's nice. And then Steinitz in 1916 proved that if I have a 3-connected graph that's planar and has at least 4 vertices, so there's that hypothesis. And again, I'm calling G prime the maximal one. Remember, G is what I started with, G prime is the maximal one. And again, I'm keeping the vertex set, I'm just adding edges. So that's the difference between G and G prime, is G prime has more edges. So anyway, I take, so here's this 3-connected planar graph with at least 4 vertices. Then Steinitz proved that G prime can be realized as the edges of a convex polytope with triangular faces. Oh, we've seen those guys. They made an appearance in the last lecture. And it turned out we know something about these. So it turns out that in this particular case, we have Euler's formula that is faces and edges and vertices, but because we have triangular faces, we also know a relation between that, and so it turns out that Euler formula just reduces this little guy in that case, and so we have this formula right here for the number of edges, and then but also we have Cauchy's theorem. Hey, this guy has triangular faces. It's rigid. So what we have is we have local rigidity and this. And basically, so what happens, I'm going to have to use the mouse to get to the right place. Well, we have a theorem that's going to tell us something. And so let's go back to one of our earlier theorems. So we had this theorem right here that said that if I'm locally rigid and have the correct number of edges versus vertices, I am independent. So here again, because remember what we just showed. We showed that we have local rigidity, we have the right number of things, and those two things give us independence. And so that theorem 3 that we did earlier, which is again part of just classic rigidity theory. So again, that's the rigidity, that's the correct bound because I'm in R3. And so that says that E prime is independent in the rigidity matroid. And it's the matroid in R3 because I now, basically, remember that even though I started in a plane, I put myself in 3-dimensional space. And so I'm now in R3. But then by Carolyn's theorem, if I'm, basically independent, that's independent. Well, E is just a subset, so that's also independent. So here's an independent subset in this, but by the Gross-Sullivan result, that's this matroid contracted by the diagonal. But then Euler's theorem says that I'm independent here, it's 4 observations. So there's the proof. So this is a really cool result. And if you think about the result, what did I use? I used statistics. I used graph. I used polytopes. I used equality of matroids. I used interesting ideals of varieties, and I used rigidity theory. So there was a lot of really great stuff lurking around here. And so what I hope to do in this lecture was convince you there's some pretty good combinatorics here, and it's richer than you might have. It's certainly richer than I anticipated, and I hope I've convinced you it's richer too. And of course, there's more. That's Jessica at 2 o'clock, and then tomorrow we'll learn something about chemical reaction networks. So thank you. So any questions? Yeah.
Maybe Jessica might mention this, but so far for matrix, we only really use the independent sets description.
Right.
Matrix has many other properties.
Right. I mean, we did use a little bit of the closure operation.
Yes.
So that snuck in.
Yeah, that's right. But other than those two, we haven't really seen anything else. Circuits. Well, almost the same thing. Is there anything with, like, say,
Yeah, so a circuit is a minimal
Minimal
independent,
dependent set.
minimal independent set, yeah.
Polynomial, like, I'll talk a little about circuit polynomial.
Yeah.
Maybe.
And I should say that I've heard the definition of matroid multiple times in my life, and it was one of those in one ear, out the other ear things. And this lecture has made a believer of me.
I've been asked to make the following question. Maybe we should all get a picture?
Hey, sounds like a good idea.
Yeah.
Because we have a couple of minutes, before lunch, so would outside be a good place?
I'm not sure.
And so we have someone who can take the picture, maybe.